Good day, everyone. And once again, your favorite uncle is back again. And we've been looking at vectors. And this time, what we want to do is to be looking at the resultant using components. So if you haven't subscribed, please just make sure that you're part of the family. And of course, you can get in touch with us whenever you need to on email. We are found on info@mlungisinkosi.co.za, Instagram @_Mlungisi Nkosi, and of course you can like and comment and share. All right, let's get right into the lesson. So we've looked at the calculation of the resultant. Okay, now I just want to go back a little bit and talk about resultants in this case. So suppose that we said a resultant, first of all, is a single vector that has the same effect as two or more other vectors combined, right? Now think about it. Suppose that we've got an object and we are applying a force. Now we can have forces that are horizontal. Okay, so suppose we're applying a horizontal force. In this case, let's just say a force of 80 newtons. Okay, and we are applying another force of, let's just say, this is going to be 40 newtons. All right. So if we wanted the resultant here, we wouldn't have a problem, because what we would simply do is choose a direction and say, well, let's choose the direction to the right as positive. You can choose any direction, by the way. I'm just going to stick to, let's say, direction to the right, or you can say eastwards as positive. So it means if I wanted the resultant or the net force here, I would simply say, well, let's call this one F1 and let's call this one F2, right? So it means I would simply say this is force F1, in this case, plus force F2. And when we add them up, they are both in the positive direction. So we would have 80 plus 40 newtons, and that would give us 120 newtons, right? So what would that 120 newtons be? It would be 120 newtons. Remember, force is a vector quantity, so we also need to state the direction. So you can either say to the right, or in this case, if we chose the points of a compass, in this case we would say eastwards, right? So that would be our resultant. So if forces are in the same dimension, we can just simply add or subtract them, right? So supposing that the same forces, again, let's say we've got F1 that was acting in that direction. Okay, so we've got force F1. Okay, again, let's just say 80 newtons in that direction. But this time we find force F2 acting in the same dimension, meaning horizontally, right? So let's say F2 acting horizontally at 40 newtons, let's say, right? But this time it is acting westwards, right? So what do we do? In this case, we'll just simply say, well, our net force or our resultant force will be F1 again plus F2, but remember, we've chosen direction to the east as positive, right? You remember that, right? So in this case, when we add the forces, the vector sum of forces, we would simply say this is 80 newtons plus a negative 40 newtons. I'm not sure why I keep writing a 4 like that. Negative 40 newtons. Why is that? Because remember, if we said westwards or eastwards rather is positive, then it would simply mean the opposite direction is negative, right? So therefore it means that in this case we'd say, well, it's 40 plus a negative 80, it's 80 rather, plus a negative 40, and that would give us 40 newtons, positive 40 newtons. So we know that the resultant in this case is 40 newtons, but in which direction? It would also be to the east. So it means if I'm looking at the result of those two forces, the resultant is actually a single force, remember, with the same effect as the two forces combined. So it means the result of these two forces acting together is just simply 40 newtons in this case eastwards, right? So that would be our resultant, right? Now, nothing wrong with that. The same would be applied if we had those forces acting vertically, right? If we had, say, for argument's sake, okay, we had a force that was acting vertically, say, upwards, okay, and it could be force, it could be distance, any vector, right? So if we had a force, let's just say, for argument's sake, that's 100 newtons upwards, and we've got another force that is acting vertically downwards, right? Let's just say that's going to be, yeah, let's just thumb suck any figure. Okay, let's say 30 newtons, right? So we've got a downward force that's acting at 30 newtons, another upward force at 100 newtons. So how do we get the resultant in this case? It simply would be, well, again, this would be the net force, would be the vector sum of forces, right? Let's call this one F, let's just give it a name. Let's say F upwards, and let's call this one the force downwards, okay? All right. So in this case, we would simply say this is the force upwards. Now I'm going to take the direction up as positive, right? In this case, plus the negative downward direction, or you can just simply say plus the force downwards. But we know that the downward force would be negative. So this would be 100 plus a negative 30. Okay, and so those would give us 70 newtons. But remember, it is 70 newtons upwards, right? So at the end of the day, we know that we would have these forces, the result of those two forces acting together, the single vector that replaces these two is just one vector, and whose value in this case is 70 newtons upwards, right? So that would be the resultant force, a single vector that has the same effect as two or more other vectors acting together. Right, you can do this whether or not you've got multiple forces, more than two, you can do this. Of course, I mean, if you had a situation where you've got two forces acting in the same dimension, okay, let's just say here we have a force upwards, and it's just acting at 80 newtons upwards, but we equally have another force acting downwards, right? Okay, let me just try to fix that. We've got a force that's acting downwards. Okay. For some reason this thing is just acting up on me. Okay, we've got a force downwards that is okay, so clearly it doesn't want to do the things. Okay, so here we are, we've got a force downwards. But if we said this force is 80 newtons as well, so what does that mean? It simply means that we now have a system that is at equilibrium. We're going to talk about that later on. I still want to address the issue of the resultant. So what does that mean? It means that if we were to calculate the resultant or the net force, please note, I'll keep using these interchangeably. One moment I'll call it the net force, the other resultant, but it's all the same thing. So in this case, it would be my force upwards plus my force downwards, and it means that we would have 80 plus a negative 80 newtons, and in this particular case, that would be 0 newtons. Okay, so that would be my resultant in the event that we've got forces that are said to be at equilibrium. Note, once I know that my resultant force, or let's say the net force or the resultant force is 0, then what does it say? It therefore means that my system is at equilibrium. Okay, so that is, in this case, the forces are said to be balanced. Okay, right. Now I want us to talk about in this case, when forces are not at either horizontal or vertical. So in this case, let's just say you've got a force that would be applied. Let's say there's my force there. Can you see, ladies and gents, it's neither horizontal nor vertical, right? So now we need to break that force down into components, right? In this case, it's going to have components, and it would be the horizontal component and the vertical component, right? So in this case, you're going to say, well, there is my force. Let's call that force force applied. Okay, yeah, I'm just going to designate it FA. Right, now when we look at the force applied, you can see that there's definitely an angle of elevation on that force. Okay, let's say that angle of elevation is theta, right? So I'm going to have angle theta over there, right? So in this case, we're going to say, well, what happens to the applied force, or FA? Then we need to break it down into its different components, right? So we find that we've got the horizontal component. Now note, it means there's a force, or rather, it means I can replace this one force, the one in blue, right, with both. In fact, let me actually take a different color for the vertical component. Okay. Yeah, let's try that again. Right, so I'm going to take, in this case, for the vertical component, I am simply going to take that force over there, right? So it means both the red and the green forces acting together, right, give us that blue force. Now let's call this one. This is the equivalent of A in the horizontal dimension, right? So meaning it's the equivalent of A, this force here, in the horizontal dimension. Please just stay with me, ladies and gents, right? And this one in green, this will be the equivalent of A in the vertical dimension. Please, ladies and gents, for the sake of time, right, I'm going to give these forces a name. Let's call this one FAX, right? If you think about the Cartesian plane, right, you have y here, you've got x there. So I'm going to call that the equivalent of A in the x dimension. And of course, the one in green, this will be the equivalent of A in the vertical, or the y dimension, right? Now, ladies and gents, I want you to please note the following, right? Again, we are back to our our 90-degree triangle, horizontal and vertical, right? We'll make a 90-degree triangle over there, right? So there's our 90-degree. So it means that we can use our trig ratios, right? Remember, the longest side, we always call this side the hypotenuse, right? Now, again, I said to you, relative to this angle theta, what is this side? This is our opposite side. So this will be the opposite side. And of course, it means that this side over here will be our adjacent side. Adjacent just simply means next to, right? So that side is next to the angle. This one we've already called the hypotenuse. Sorry about that. We've already called the hypotenuse. So this one becomes the adjacent side. Now, what we said is, if you take the sine of any angle, right, the sine of theta, in this case, which is our angle, will become opposite over adjacent, okay? Over hypotenuse. What am I saying now? Over the hypotenuse, right? We use the mnemonic there, so, okay? So that's opposite over hypotenuse. But remember, what is our opposite side in this case? It's going to be our vertical component, right? So which means the sine of angle theta is opposite, which is FAY, which is our vertical component, right? Divided by the hypotenuse, which is our original force FA, right? So now let's do this. I'm going to write it as a fraction. So what it means is that we can cross multiply, right? So it means FAY multiplied by 1. So it means, which means the vertical component of y, or rather the vertical component of the force FA is going to be FA, the sine of angle theta. Please, ladies and gents, I want you to be mindful of that, right? So remember, if I want to find the vertical components, the vertical component in this case, I will simply say it's FA, the sine of the angle of elevation, right? Similarly, if I wanted to find the horizontal component in this case, so I am going to say, well, the cos of angle theta. Please remember, in this case, what is cos? That's adjacent. Okay, let me write that nicely. That's going to be adjacent over hypotenuse, right? So in this case, I know I use the mnemonic, or an easy way to remember that. So that's cos of theta. What is our adjacent? Okay, our adjacent side, that's going to be FAX, right? That is the horizontal component, and divided by FA, right? So it means, which means that FAX, if I cross multiply again, FAX times 1, that's FAX, and then that's going to be FA, the cos of angle theta. So ladies and gents, I want you to keep that in mind. Whenever we've got a force that is acting at an angle, we can break it down into its horizontal and vertical equivalents. Right, now in this case, I want us to take a question, right, that we can use to calculate the resultant using, in this case, the components. All right, so let's have a look at this example. Right, they say that calculate the resultant of the forces in the diagram. Of course, we're going to use components in this case, right? So here we are. We've got a diagram. We've got two forces there. So what we're going to do is we're going to resolve them into their different components, and thereafter just simply calculate the resultant from there. Right, now, what's the first thing that we're going to do? Of course, if we're using the previous methods, what we would try to do is complete a parallelogram and, complete a resultant, or rather calculate the resultant from that. Okay, but now what we're going to do is let's work with each force. I'm going to start with force F1, right? And on force F1, okay, let me just go back to its original color. Right, so on force F1, which is a force in that direction, it seems my lines are not cooperating today. Right, so which is a force in that direction, right? So it's a force F1, okay, and it's got 200 newtons, right? Now, what we're going to do is resolve force F1 into its horizontal component. Okay, so there's my horizontal component there. But I'm also going to resolve it into its vertical component, which is upwards. So if you think about it, that force in green and that force in red, right, are equivalents of F1 in the horizontal and the vertical dimension. I hope that makes sense, right? So this I'm going to call F1x, okay? Maybe just for the sake of continuity, let me write that in green, okay? So I'm going to say this is F1 in the x dimension, and of course this will be F2, F1 rather, in the y dimension, the vertical and the horizontal component of the force. But we know in this case that we said the angle of elevation was 40 degrees, right? So F1 is elevated 40 degrees in this case from the horizontal, right? So now what we're going to do is let's work out what is F1x. Okay, so we said let's work out F1x. So what I'm going to do is I'm just going to calculate F1x and F1y. So F1x would be, in this case, remember we are going into the horizontal dimension, right? This is the adjacent side, that's the hypotenuse. So it's simply going to be F1, the cos, okay? So the cosine of 40 degrees, right? So that would be 200, the cosine of 40 degrees, right? Let's get our calculator and find out. So that's 200, the cosine of 40 degrees. So ladies and gents, I'm just going to keep my answers to 2 decimal points. Those of you that are at university can actually talk about significant figures in this case. Right, I won't consider that much for now. So that's 153.21. That's our horizontal dimension, right? And in this case, we're looking for, again, the vertical dimension, meaning the equivalent of that force in the vertical. So that's F1y, right? The one in red. So this is simply going to be, in fact, let me write it there. F1y, the vertical dimension. So this is simply going to be F1, the sine of the angle of elevation, and that's 40 degrees. So that's going to be 200 sine of 40, right? So in this case, you've got 200, the sine of 40, and I get 128.56. So that's 128.56 newtons. Of course, you'll work it out so that you see if you get the same value. Now, what we're going to do, ladies and gents, is we're going to do exactly the same for F2, right? F2 is a force in that dimension, okay? So it's a force in that dimension, right? And we knew that that force is 150 newtons. So that's our F2. And what we do know is that it was elevated in this case by 25 degrees, right, from the horizontal. So in this case, we know that this, we're going to use, there's our F2y, and that is going to be our F2x, right? All right, so now let's calculate our forces. We know it's elevated by 25 degrees, so that's going to be, so it means if I want to find the horizontal dimension, right, in red this time, okay, so it means for the horizontal dimension of F2, that's going to be F2, the cos, sorry about that, so that's going to be the cos of 25 degrees, so that's going to be 150 cos of 25, right? And that gives us, so that's 150, the cosine of 25, and that gives us 135.95 newtons, right? And then the next one we've got F2, which is in green, F2y, which is F2 the sine of 25, and that's 150 sine 25, right? And in this case, that's 150 sine of 25, and we've got 63.39 newtons, right? That's F2 in the vertical dimension. Now, ladies and gents, what we've done now is to break both forces into their respective horizontal and vertical dimension. Now, let me just draw a graph, or rather a diagram, showing you what this actually kind of looks like. So I have replaced both forces, right? Now let's go back to F1. I have replaced both forces with both the red and the green. So it means that instead of drawing that F1 in blue, I'm going to draw the red and the green, right? So I know that I've got a force that is going vertically up, okay? I had drawn it in red, right? I said that's the force that's going up. That's F1y. So we are taking the red, okay, as well as the green. So in this case, it means that those are the two components that we are now going to consider, right? So remember, we said we've got that vertical component. I believe that's the one that was in the red, right? Yes. So, and we know that we had a vertical component that was in the green going that way, right? Now, the respective values, the one in the red we said was 128.56, 128.56, right? In fact, let me just write it this side. 128.56, okay? All right, let me just try and write it nicely. 128.56 newtons, okay? And the one in the green we said was 153.21. So 153.21. Okay, right. So this is a very rough sketch, ladies and gents. So I just want us to, for the sake of, being able to see what we're doing. All right, and then let's go to force F2. We said we've got the one in the red was the horizontal force, right? That's 135. So this time, the one in the red going that way, that was 135. I might need to adjust my drawing a bit. 135.95, right? And then we had another force. We had indicated it in green, which was the vertical dimension. It's 63.39. So that's 63.39 newtons, right? So now, so that is what we have. Now notice what I've actually done. I have broken this drawing down into horizontal and vertical components. So what I'm trying to do here is that I can see that our value is, so I'm trying to make this slightly longer, okay, so that we can see that, right? So there we go. So we said our value was 153.21, right? So that's 153.21. Now, ladies and gents, once we've done that, okay, it means now we can work out the resultant. Now, remember, in this case, we're going to say, right, what is the resultant in the horizontal dimension, right? So I'm going to say F net in the x direction. So meaning I'm going to consider these two. So now what I need to do is I need to choose a direction in the horizontal. I see this one is bigger, right? F1x, right? So in this case, F1x is bigger, right? So I'm going to choose direction that way as positive. So it means that in the horizontal dimension, right, your F net will be F1x plus a negative F2x. So it means this is F2x in this case. So that would be 153.21 minus 135.95. And so let's take that quickly. So that's 153.21 minus 135.95. Okay, so that gives us 17.26. Now I want you to be very careful, ladies and gents, right? In which direction is that force? It will definitely be it's a positive answer, so it's telling me to the left, right? Or you can say to the west. Okay, right. So if you take points of a compass, so that's west, that's east, and that's south there. Okay, the way in which I remind myself every time is say we. Okay, so in this case I know we, so that's west on the left hand side and east on the right hand side. Right, so in this case I'm going to say right. So it means that in the x direction I've got only one force, right? I want you to notice that I've got only one force, which is in that direction. I'm now drawing it in the yellow, which is 17.26. I hope that makes sense, ladies and gents, right? And then let's take the vertical dimension, right? Now notice you've got two forces that are in the same direction, right? So it means in this case, I am simply going to say, right, so both of those forces are acting vertically upwards. Okay, so I'm going to make this a head to tail drawing. Right, so both of those forces are acting vertically upwards. Right, and what is their result? Their result is that, so I'm taking F net in the y dimension. That's going to be F1y plus F2y, right? So in this case, my F1y was 126.56 plus, in this case, we have that for 63.39. Okay, so let's add those up. All right, so that's 126.56 plus 63.39. Okay, so it means that our force is 189.92 newtons. All right, so we know that we've got a force there, and our force is going to be 189 rather, 0.92, sorry about that, 189.92 newtons. All right, in this case, I want you to please note that you could have actually drawn, in this case, you're drawing in this way. You could have said you've got your force there in the horizontal dimension, right? And you've got another force there. Okay, that's a little bit skew. Well, not a little bit, actually, it's quite skew. Okay, so you can say you've got your force there. Yeah, I'm going to try by all means, right? So you've got your force there. Now, what would be the resultant? We said a single vector, right? With the same effect as both vectors combined. So there's your resultant over there, right? Even if you took the one that I have here in yellow, right? Your resultant would be same thing, right? So you would have your resultant over there. So the direction actually does not change. All right. So I hope that makes sense. So this would be F net. Let me just for continuity, let's just make sure we maintain. Right. So in this case, I've got F net in the X direction, right, which was 189. Which was 17. That's in the Y dimension. That's in the Y dimension. And this is F net in the X dimension, which was 17.26. Right. Ladies and gents, what I want to do is I want us to try and calculate that quickly, and so that we can get to the conclusion of this. Now, how do I work out the net force, the resultant force? You remember this is a 90-degree triangle. Whether you take this one or that one, both of them are exactly the same thing, right? So this is 189 over here, 0.92 newtons, right? So in this case, what do I do? So it means that F net squared, square of the hypotenuse, sum of the squares of the other two sides. So that's F net in the X dimension squared plus F net in the Y dimension squared. So that would be in the X dimension, we've got 17.26 squared plus 189.92 squared, right? And in this case, all we simply do is to calculate. So 17.26 squared plus we've got 189.92 squared, and in this case that's the answer we get. And please remember, we need to take the square root of that, so we're going to say square root of our answer. So it means that our net force is 190.70. Okay, so I'm going to leave it as 190.7. That is the value of our F net. But remember, in this case, we also need to state the direction. Okay, so we can either calculate this angle over here, or we can calculate that angle over there, right? So I'm going to go with this drawing, if you don't mind, right? So I am going to say, right, so we're looking for the angle. Okay, let's call it alpha. So that's going to be the opposite side. That's the adjacent side. So I'm going to use 10. So the 10 of alpha will be opposite over our adjacent, right? So what is our opposite side? It's going to be our our Y component, which is 189. So that's going to be F net Y over F net X. So remember, that's 189.92, right? Divided by 17.26. Okay, so now it means, which means if we want to get alpha, we'll say the arctan of that entire value, 189.92 divided by 17.26. Okay, so let's do that quickly. So that's the arctan of 189.92 divided, so that's divided by 17.26, and we get an angle of 84.81, right? Now, we can express that our net force will be equal to the value of our net force, 190.7, okay, newtons at, now remember that angle there, my reference is to the west. Okay, from the west I am going to move that angle 84.81 towards the north. Okay, so from the west I'm moving that angle towards the north. Okay, so it's going to be 84 at west, 84.81 north. Okay, or you can simply say that's 190.7 newtons north of at 84.81 degrees north of west. Okay, if you do want to use the bearing, ladies and gents, you can appreciate that. Remember, bearing is from the north line, you measure it clockwise, so that would be 90 till there, that would be 180 till there, that would be 270 till there, and an additional 84.81, I believe. So if you wanted to use bearing, you can say at a bearing of so that would be 270, so that's 270 plus 84.81, so that would be 354. So this would be a bearing of 354.81. Okay, right. So ladies and gents, I hope you have an appreciation for this. Okay, and in this case, we'll continue with some more examples that have to do with the resultant as well as calculating the equilibrium. Sorry that this took so long, but it had to be explained in a clear manner. So in this case, you could have done the same, by the way. You could have found this angle here and then expressed from the north, you're going that many degrees towards the west. Okay, either way, you would have actually got into the same answer. In this case, ladies and gents, I want to leave it here, and hopefully you understood, okay, working with components, and we're going to continue with this. Otherwise, from me for now, I'll see you guys next time, and please don't forget to subscribe and tell as many people as possible that your favorite uncle is doing the most. I'll see you guys next time. Sharp, sharp.